During the fighting in Sicily in the summer of 1943, German forces captured American radio equipment that would force them to confront an uncomfortable truth. Among the seized items was a small olive-drab box with a telescoping antenna that doubled as the power switch. It fit in one hand, 5 miniature vacuum tubes, a single quartz crystal for frequency control. The entire unit weighed less than 5 pounds. German signals experts examined the captured equipment and compiled a formal evaluation. They described the American handheld radio as extremely effective. Its lightweight, small size, efficiency, and range made it ideal equipment for forward observers and companies. They had nothing like it. 7,000 miles away, in a factory at 4545 West Augusta Boulevard in Chicago, a Polish refugee engineer named Henryk Magnuski was refining circuit designs for an even more advanced radio. This one was a backpack unit that used frequency modulation instead of amplitude modulation. It could cut through the static of tank engines and artillery explosions. It could reach 8 miles over open terrain, and American factories were producing them by the tens of thousands. The German experts examining that captured handheld radio did not yet fully understand what they were looking at. They were looking at the reason Germany would lose the war. The misjudgment began long before the first shot was fired. German military intelligence compiled reports on American industrial capacity and technological capabilities throughout the 1930s. The conclusions were remarkably consistent. America was a nation of businessmen and consumers, not engineers and warriors. Its factories made automobiles and refrigerators, not precision military equipment. Its people had grown comfortable during the long peace and lacked the technical discipline required for modern warfare. Hitler himself shared this contempt for America. In January 1942, just weeks after Pearl Harbor, he told his inner circle that he did not see much future for the Americans. It was a decayed country, he said. They had their racial problem and the problem of social inequalities. How could one expect a state like that to hold together? His dismissiveness reflected a broader German failure to take American capabilities seriously. Hermann Göring, head of the Luftwaffe and one of Hitler's closest confidants, dismissed American production claims as fantasy. When President Franklin Roosevelt announced in May 1940 that the United States would produce 50,000 aircraft per year, the German High Command laughed. In 1939, American military aircraft production had been fewer than 3,000 planes total. The idea that this could increase by a factor of nearly 20 seemed absurd. German planners dismissed American claims of industrial potential as propaganda. When they examined American military equipment in the years before the war, they found it adequate but unremarkable. American tanks were thinly armored. American aircraft were competent but not exceptional. American artillery was conventional. Nothing suggested that America possessed any decisive technological advantage in the areas that Germans considered important. They were measuring the wrong things. They looked at tanks and aircraft and artillery, the visible symbols of military power. They did not look at the invisible infrastructure that made modern armies function. They did not understand that a radio small enough to fit in a soldier's hand could matter more than a tank regiment. The story of American radio superiority begins not on a battlefield, but in a university laboratory. In 1930, a Columbia University professor named Edwin Howard Armstrong filed a patent application that would reshape military communications forever. The patent was granted on December 26, 1933. Armstrong was already one of the most celebrated inventors in America. During the First World War, while serving as a Signal Corps captain in Paris, he had invented the super heterodyne receiver, the circuit design that would become the foundation of virtually every radio built for the next century. He had also invented the regenerative circuit and the super-regenerative circuit. 3 of radio's 4 fundamental innovations came from his mind. But his 4th invention would prove the most consequential. Armstrong called it wideband frequency modulation, or FM. Instead of varying the amplitude of a radio wave to carry information, FM varied the frequency. The difference seemed technical and obscure. It was neither. Conventional AM radio worked by varying the strength of a radio signal. A stronger signal represented one part of the sound wave. A weaker signal represented another part. This approach was simple and well understood, but it had a fatal flaw. Any source of electrical interference, from lightning to engine ignition to nearby machinery, could affect the amplitude of a signal. The interference blended with the intended transmission, creating the static that plagued every AM broadcast. FM worked differently. Instead of varying amplitude, it varied the frequency itself. The receiver was designed to respond only to frequency changes, ignoring amplitude variations entirely. This meant that electrical interference, which affected amplitude, was simply filtered out. On November 6, 1935, Armstrong stood before the Institute of Radio Engineers in New York and demonstrated what FM could do. He transmitted sounds that were unrecognizable on conventional AM radio. A glass of water being poured, paper being torn, the rustle of fabric, a piano playing with crystal clarity. The audience sat in stunned silence. They had never heard such fidelity from a radio transmission. Armstrong's FM eliminated the hiss and crackle that plagued every AM broadcast. It stripped away interference from electrical equipment, engine ignition systems, and atmospheric static. The demonstration marked the beginning of a revolution in radio technology. The implications for military communications were profound. A battlefield is the worst possible environment for radio. Tank engines generate massive electrical noise from their ignition systems. Artillery explosions create electromagnetic pulses. Aircraft engines crackle with interference. Weather conditions change constantly. AM radios in combat were plagued by static so severe that operators often could not understand transmissions. Messages had to be repeated multiple times. Critical information was lost in the noise. FM changed everything. Its limiter circuits stripped out amplitude-based noise. Its capture effect locked onto the strongest signal while suppressing interference. Its squelch circuits meant operators no longer had to listen to constant static between transmissions. Communications became clear and reliable, even in the worst conditions imaginable. In 1938, Colonel Roger Colton, director of the Signal Corps Laboratories at Fort Monmouth, New Jersey, made what Armstrong himself called the most difficult decision of the history of radio, which anyone was ever called upon to make. Colton directed that all future American military radios would use frequency modulation. The decision was controversial. FM required more complex circuitry than AM. It demanded more precise manufacturing. It used wider bandwidth. Many engineers argued that the added complexity was not worth the benefits. Colton overruled them. He understood what FM meant for soldiers in combat. Armstrong was so committed to the war effort that he offered free use of all his FM patents to the War Department for the duration of the conflict. America would go to war with the most advanced radio technology on Earth, and its inventor asked nothing in return. The German military made a different choice. They stayed with amplitude modulation. This decision reflected deeper differences in how the two nations approached electronics. Germany had excellent radio engineers. Companies like Telefunken, Lorenz, and Siemens produced sophisticated equipment. Their radios were well built and ruggedly constructed. German tubes were standardized for easy replacement in the field. The RV-12P 2000 Universal Pentode became the standard Wehrmacht receiver tube, produced in enormous quantities. German military culture emphasized reliability through simplicity. They preferred proven technology over untested innovation. The Wehrmacht had won stunning victories in Poland, France, and the early campaigns in Russia using AM radios. Blitzkrieg had conquered most of Europe. Panzer divisions had sliced through enemy defenses with devastating speed. German communications, while not perfect, had been adequate to coordinate these operations. Why change what was working? But German success had obscured a critical weakness. Their early victories had been won against enemies who were surprised, unprepared, and often technologically inferior. The Poles had obsolete equipment and were overwhelmed in weeks. The French were caught off balance by the speed of the German advance and collapsed before they could recover. The Soviets in 1941 were reeling from purges that had gutted their officer corps and were pushed back hundreds of miles in the first months of fighting. German communications had been adequate against these opponents. Radio static was an annoyance, not a decisive handicap, when fighting enemies who were already beaten. But the Germans had not yet faced an enemy who could match their tactical proficiency while possessing superior communications technology. They would soon discover what that meant. The American radio industry had grown up serving a vast civilian market. By the early 1940s, Roughly 90% of American households owned a radio receiver. This massive market drove companies to compete on size, cost, and performance. Vacuum tubes became smaller as manufacturers sought to build portable receivers. Manufacturing became more efficient as volume production drove down costs. Engineers learned to pack more capability into less space because consumers wanted radios they could carry. When war came, this expertise translated directly into military advantage. Germany had no equivalent market pressure. Their radio industry served a smaller civilian population and faced less competitive pressure to miniaturize. German tubes were well engineered but sized for stationary or vehicle-mounted equipment. When German engineers designed military radios, they built them to military specifications using military methods. They did not have decades of consumer electronics experience teaching them how to make components smaller, lighter, and more reliable. The gap became visible in the first months of American combat operations. The contrast between expectation and reality would prove devastating for German strategic planning. In November 1942, American forces landed in North Africa as part of Operation Torch. It was the first major American ground combat of the war, and communications problems immediately revealed themselves. Artillery forward observers spotted enemy movements, but could not reach gun lines in time because their radios failed under battlefield conditions. The static was overwhelming. Transmissions broke up. Messages had to be repeated endlessly. Infantry units lost contact with supporting armor. Coordination between ground forces and aircraft broke down repeatedly. The army, it was later said, paid for many communications shortcomings in blood. The failures at Operation Torch would not be repeated. The solution was already in development back in Chicago. In 1940, a Connecticut engineer named Daniel Noble joined Galvin Manufacturing Corporation as Director of Research. Noble had previously designed the world's first statewide two-way FM radio system for the Connecticut State Police. He understood what FM could do in practical field conditions, not just laboratory demonstrations. When the Signal Corps issued a contract for a new portable AM radio, Noble objected strenuously. He told Colonel J.D. O'Connell bluntly that he felt this was a grave mistake and that the area of development should be for an FM portable unit. Noble argued that AM was fundamentally unsuited for battlefield conditions. No amount of engineering could overcome the laws of physics. Only FM could deliver reliable communications in combat. O'Connell was convinced. The contract was redirected. Noble assembled a team of brilliant engineers at the Galvin factory on Augusta Boulevard in Chicago. His principal radio frequency designer was Henryk Magnuski, a Polish-born engineer who had graduated from Warsaw University of Technology in 1934. Magnuski had come to America before the war to continue his education and was still in the country when Germany invaded Poland in September 1939. He could not go home. His family was trapped behind enemy lines, facing the brutality of Nazi occupation. Magnuski channeled his anguish into work. He threw himself into the radio project with an intensity that impressed even his driven colleagues. Working 18-hour days in the Chicago factory, he refined circuit after circuit. The radios he helped design would contribute to the liberation of his homeland. Every technical problem he solved brought that liberation closer. The team also included Marion Bond, Lloyd Morris, and Bill Vogel. They worked long hours in conditions that would later be described as frantically intense. The war was going badly in late 1941 and early 1942. American forces were being pushed back across the Pacific. German submarines were sinking ships faster than American shipyards could build them. Every day of delay in delivering better equipment meant more American soldiers dying with inadequate communications. By spring 1942, the team had 2 working prototypes of what would become the SCR-300. They first tested the radios in Chicago, transmitting between the Tropic Air Building roof and Thatcher Woods Forest Preserve. The results exceeded every expectation. The specification called for 3 miles of range. The prototypes achieved 8 miles. The team then took the radios to Fort Knox, Kentucky, for formal acceptance testing before Signal Corps and Infantry Board officers. These were hard-headed military professionals who had seen countless promising technologies fail under field conditions. They were skeptical of claims from civilian engineers. The demonstration drew what was described as an unusually enthusiastic response from the hard-headed infantry and Signal Corps officers who witnessed it. They understood immediately what this technology meant for soldiers in combat. The SCR-300 operated on FM at 40 to 48 MHz across 41 channels. It used 18 miniature vacuum tubes in a sophisticated double super heterodyne receiver, the same circuit architecture that Armstrong had invented in Paris during the First World War. A single tuning control adjusted both transmitter and receiver simultaneously, simplifying operation under the stress of combat. An automatic frequency control circuit ensured clear communication without precision tuning, compensating for the frequency drift that plagued less sophisticated radios. The entire unit weighed approximately 38 pounds with the standard battery and delivered roughly 20 to 25 hours of battery life. A single soldier could carry it on his back and operate it while moving. This mobility was revolutionary. Previous infantry radios had required multiple operators and could only be used from fixed positions. The SCR-300 went where the soldier went. Nearly 50,000 SCR-300 radios were produced during the war. The first units saw combat in the Pacific at New Georgia in August 1943. Colonel Francis Ankenbrandt reported it was exactly what is needed for frontline communication in this theater. The dense jungle canopy that blocked conventional radio signals posed fewer problems for the FM sets. In Europe, the first units were airlifted for the invasion of southern Italy at Salerno in September 1943. But the SCR-300 was not the radio that German officers found in Sicily. That distinction belonged to an even more revolutionary device, the SCR-536. The idea came from watching a National Guard exercise in the late 1930s. Don Mitchell, chief engineer at Galvin Manufacturing, observed how vehicle-mounted radios were abandoned in mud and confusion when troops had to move on foot. Commanders lost contact with their men the moment they left their vehicles. Mitchell returned to Chicago convinced that military communications had to follow man to the greatest degree possible. He began designing a radio that could be carried in one hand, like a telephone. The concept was radical. No one had ever built a two-way radio small enough to hold like a telephone handset. The engineering challenges were immense. The device had to transmit and receive voice clearly over useful distances while running on batteries small enough to fit inside the handset. Every component had to be miniaturized beyond anything previously attempted in military equipment. Mitchell and his team solved problem after problem. They used 5 miniature vacuum tubes, each smaller than a thumb. These tubes were products of the American consumer electronics industry, developed for portable civilian radios and now repurposed for war. They designed a 40-inch telescoping antenna that doubled as the power switch. Pull it out to turn the radio on, push it in to turn it off. The mechanism was simple enough that a soldier could operate it in complete darkness or while under fire. The entire unit weighed just 5 pounds, including batteries, and could transmit voice up to 1 mile over land, 3 miles over salt water. It operated on AM rather than FM, which limited its noise immunity. But the compact size and light weight made it invaluable for situations where the larger SCR-300 was impractical. The Signal Corps initially dismissed the SCR-536 as a stopgap radio because of its limited range, but paratroopers needed something lightweight enough to carry during combat jumps. Every pound mattered when you were floating down under a parachute into enemy territory. The little handheld radio found its mission. By July 1941, the SCR-536 was in mass production. Approximately 130,000 units were manufactured during the war by Galvin Manufacturing and other firms, including Electrical Research Laboratories of Evanston, Illinois. The SCR-536 first saw combat during Operation Torch in November 1942. Within months, it was in the hands of every American infantry company, and in Sicily, it fell into German hands. The German analysis of the captured equipment must have been sobering. Their own portable radios were larger, heavier, and less capable. The closest German equivalent to the SCR-300 was the Tornisterfunkgerät, D2. It operated on AM at 33.8 to 38 MHz, with approximately 1 watt of power and roughly 3 kilometers of voice range. Unlike the one-man SCR-300, the German Tornisterfunkgerät, D2, was typically split between 2 soldiers for transport. One carried the transceiver. The other carried the battery and power supply, connected by cable. If the 2 soldiers became separated in combat, the radio was useless. If the cable was severed by shrapnel, the radio was useless. The system was cumbersome, vulnerable, and far less mobile than its American counterpart. For company and platoon-level communication, Germany fielded the Feldfunksprecher series. These were smaller, single-soldier portable radios, but the United States Signal Corps obtained and analyzed them in detail. Their classified assessment, published in Tactical and Technical Trends No. 43 in January 1944, delivered a devastating comparison. The distance over which satisfactory operation may be expected from the German sets is theoretically about 1/4 the distance over which the American sets can operate. 1/4 the range. The German radios could reach perhaps 500 meters reliably. The American SCR-536 could reach a mile. The SCR-300 could reach 8 miles under good conditions. This was not a marginal difference. It was a fundamental asymmetry that shaped how the two armies could fight. Germany had no equivalent to the handheld SCR-536 at all. The IEEE spectrum confirmed that the Axis powers apparently never had the equivalent of the SCR-536. Germany's closest attempt, the Kleinfunksprecher D, codenamed Dorette, was developed by Philips and entered service only in October 1944, more than 3 years after the American radio entered mass production. Even then, the Dorette was a two-piece system requiring separate radio unit and battery box, with external headphones and a throat microphone. It was not a true one-piece handheld. Its production was repeatedly disrupted by Allied bombing of Philips facilities in the Netherlands, and surviving examples show visible decline in component quality as the war progressed and materials became scarce. The quartz crystal gap compounded German disadvantages. Every modern radio depends on quartz crystals to maintain precise frequency control. Without crystal control, radio frequencies drift as components warm up, making it difficult to maintain contact and impossible to operate in dense channel environments. The United States scaled crystal production from roughly 100,000 units per year in 1939 to approximately 30 million per year at peak wartime output. Total wartime production reached tens of millions of crystals, representing one of the largest scientific manufacturing undertakings of the war. American industry solved manufacturing problems that had seemed insurmountable, developing new cutting techniques and quality control procedures that multiplied output 100-fold. Germany, cut off from Brazilian quartz deposits by Allied naval blockade, produced only a fraction of what America manufactured. Göring's autarky policies had emphasized domestic production of strategic materials, but Germany had no significant quartz deposits. This forced German radios to rely more heavily on free-running oscillators rather than crystal control, resulting in less stable frequency management and inability to operate in the dense, channelized frequency environment that American FM radios navigated effortlessly. The tactical consequences of this communications gap were visible on every battlefield where American and German forces met. By Normandy, every rifle company of the United States, 29th Infantry Division, carried 6 SCR-536 radios, 1 for each of 3 rifle platoons, 2 for the weapons platoon, 1 for the company commander. At battalion to regiment level, SCR-300 backpack radios provided reliable FM voice links. American infantry could coordinate in real time at every level of command. A platoon leader under fire could speak directly to his company commander. A company commander could speak to battalion headquarters. Information flowed up and down the chain of command in seconds. Standard German organization placed radio only at company level and above. Platoon leaders communicated with their company headquarters by runners, wire, or visual signals. If a German platoon leader needed to report enemy movement, he sent a man running across open ground, exposed to fire. If an American platoon leader needed to report enemy movement, he spoke into a handheld radio, and the information reached his commander in seconds without exposing anyone to additional danger. This difference was measured in lives. The American Fire Direction Center system exploited this radio advantage to devastating effect. Forward observers, averaging roughly 21 years old, advanced with the infantry and transmitted target coordinates via FM radio to centralized fire direction centers behind the lines. These centers converted the data into firing solutions and could mass fire from multiple batteries onto a single target in minutes. A young lieutenant with a radio and a pair of binoculars could bring down the fires of an entire artillery battalion on enemy positions almost instantly. He could adjust fire in real time, walking shells onto targets that tried to move. He could shift fire from one objective to another without delay. This responsiveness was impossible without reliable radio communications. The FM radios were critical because noise immunity was essential. Forward observers often called in fire support while sheltering behind tanks, crouching in shell craters, or advancing under fire. Engine noise, explosions, and electrical interference surrounded them constantly. An AM radio would have been useless in such conditions. The static would have drowned out every transmission. The FM radios cut through the chaos and delivered clear voice communications regardless of battlefield conditions. General George Patton observed that artillery won the war. He was describing this integrated radio artillery system. American artillery became the most feared element of United States combat power precisely because radio made it responsive and precise. German soldiers learned to dread the moment when American artillery began to fall. It came too fast, too accurately, and too heavily to escape. The German experience at Kasserine Pass in February 1943 should have provided ample warning of American potential. Field Marshal Erwin Rommel's Afrika Korps tore through inexperienced American positions. Units broke and ran. Equipment was abandoned. American casualties exceeded 6,000 men. The United States Second Corps lost 183 tanks, 104 half-tracks, 208 guns, and 512 trucks. Approximately 3,000 men were captured, many of them in the first chaotic days of the German breakthrough. But what happened next revealed something the Germans failed to appreciate. The Americans recovered with startling speed. Within weeks of the disaster, they reorganized their forces, relieved incompetent commanders, and implemented brutal lessons learned. General George Patton took command of the demoralized Second Corps and transformed it through sheer force of will. Patton imposed discipline with ruthless intensity. He demanded standards that seemed unreasonable to men who had just been routed. But he also listened to what had gone wrong and fixed the problems systematically. Tactics improved, coordination tightened, air support became more effective, communications procedures were revised based on actual combat experience. The American military possessed an institutional commitment to learning from failure that the Germans never fully understood. After Kasserine, the Army's Ground Forces commander conducted a comprehensive review of what had gone wrong. His findings were sent back to training camps across the United States, where they shaped the preparation of divisions that had not yet deployed. The mistakes of February 1943 became the curriculum of March 1943. By May 1943, 3 months after Kasserine, the war in North Africa was over. 275,000 German and Italian soldiers marched into prisoner of war cages, more than had surrendered at Stalingrad. The Americans who had panicked at Kasserine were now among the victors. The fighting in Sicily that summer provided the first clear evidence that German forces recognized American radio superiority. SCR-536 units were captured and examined by German signals specialists. By some accounts, SCR-300 sets fell into German hands as well. The German signals establishment had to confront an uncomfortable reality. The enemy possessed communications technology that Germany could not match and could not replicate. The evidence of German appreciation for American equipment became explicit during Operation Greif in December 1944. SS Obersturmbannführer Otto Skorzeny, the famous commando who had rescued Mussolini from captivity, attempted to equip Panzer Brigade 150 with captured American vehicles, weapons, and equipment for a deception operation during the Battle of the Bulge. His men would wear American uniforms and drive American vehicles to spread confusion behind Allied lines. Skorzeny encountered an unexpected obstacle. German frontline units that had captured American equipment found it better than German equipment and refused to surrender much of it. Combat soldiers who had used captured American radios, vehicles, and weapons knew from experience that the equipment was superior. They were not willing to give it up for a special operation, no matter how important. Skorzeny obtained only a fraction of what he needed. 4 scout cars instead of armored vehicles, 30 jeeps instead of tanks, 15 trucks instead of the planned armored force. Operation Greif achieved some tactical success in spreading confusion, but it never reached its ambitious objectives. partly because combat units would not relinquish their captured American gear. The most authoritative German assessment of American radio capabilities came after the war. In March 1950, General der Nachrichtentruppe Albert Praun wrote a 250-page report for the United States Army Historical Division titled German Radio Intelligence. Praun was the last Chief of Army and Armed Forces Signal Communications, appointed on November 1, 1944, after his predecessors Erich Feldgiebel and Fritz Thiele were executed for involvement in the July 20th plot against Hitler. Praun had survived the war and the purges. He had commanded German signals troops from the Eastern Front to the final collapse. He understood better than almost anyone what American radio superiority had meant on the battlefield. His report, originally classified confidential and later declassified by the National Security Agency, dedicates Chapter 4, Section 3, specifically to appraising United States Army radio communications. The full document is available from the NSA's declassified Friedman Documents collection. Praun's structural choice, devoting a formal appraisal section to American radio capabilities alongside evaluations of Soviet and British systems, reflects the seriousness with which Germany's senior signals officer regarded American communications technology. This was not a minor factor in German defeat. It was significant enough to warrant formal analysis decades after the war ended. The industrial base that produced these radios had no Axis equivalent. Galvin Manufacturing Corporation, founded by Paul Galvin and his brother Joseph in Chicago in 1928, he had started by making battery eliminators for home radios before creating the Motorola brand for car radios in 1930. The name combined motor and ola, meaning sound in motion, reflecting the company's focus on mobile electronics. By 1936, Paul Galvin returned from a tour of Europe convinced that war was imminent and directed company research toward military applications. He saw what was happening in Germany and understood that America would eventually be drawn into the conflict. When war came, Galvin Manufacturing was already prepared to produce military equipment. Galvin competed against Hazeltine, Wilcox Gay, and Philco at the Fort Knox acceptance trials for the SCR 300 contract. They won on the strength of their FM design and their demonstrated capability to produce complex electronics at scale. During the war, the company produced nearly 50,000 SCR 300 units and was the primary manufacturer of the 130,000 SCR 536 units. But the effort extended far beyond one company. Raytheon mass-produced miniature and sub-miniature vacuum tubes. They built approximately 80% of all magnetrons for radar and produced tubes rugged enough to survive being fired from a cannon inside proximity fuses. RCA pioneered the miniature tube format that made handheld radios possible. Western Electric, the manufacturing arm of AT&T, supplied tubes and components on an enormous scale. Sylvania developed ultra-low power filaments critical for battery-operated equipment. The Signal Corps engineering laboratories at Fort Monmouth, New Jersey, employing about 14,000 personnel during the war, coordinated the entire development pipeline. The adjacent Camp Evans facility housed the Joint Army-Navy Tube Standardization Laboratory and served as the primary center for radar development. Fort Monmouth's labs had been experimenting with FM transceivers since 1936, laying the groundwork for the rapid development that followed. America's civilian radio culture provided irreplaceable human capital. By 1939, approximately 51,000 Americans held amateur ham radio licenses. These hobbyists understood radio technology from practical experience. They had built their own equipment. They had troubleshot problems. They had developed intuitive understanding of radio propagation. When wartime amateur transmissions were suspended, these operators flowed directly into the military as radio technicians and signal officers. They brought practical expertise that no training program could replicate. Germany had nothing comparable. The Nazi regime had restricted amateur radio activity, viewing it as a potential security threat. German soldiers received formal training, but they lacked the hands-on experience that came from years of amateur operation. At D-Day, the Signal Corps faced an unprecedented challenge. The invasion of Normandy would require coordinating the largest amphibious assault in history across 5 beaches, spanning 50 miles of coastline. Thousands of aircraft would provide air support. Hundreds of naval vessels would bombard shore defenses. Tens of thousands of soldiers would land in the first wave alone. Every element of this massive operation needed to communicate with every other element. The Signal Corps estimated it needed approximately 90,000 transmitters for Operation Overlord. Radio channels outnumbered available frequencies 7-1. The electromagnetic spectrum over the Normandy beaches would be more crowded than any battlefield in history. If radios interfered with each other, if frequencies drifted and overlapped, the entire operation could dissolve into chaos. The solution, narrowing guard bands between channels to as little as 4 kilocycles, was enabled by crystal-controlled FM precision. Without crystal control, transmitters would drift into adjacent channels and create interference. With crystal control, frequencies stayed exactly where they belonged, and thousands of radios could operate simultaneously without mutual interference. The 71 million quartz crystals that American industry had produced made this possible. German radios, lacking crystal control in sufficient quantity, could never have managed such dense channel allocation. It worked. In the first 3 weeks after the landings, only about 80 interference complaints were registered among all transmitters. This was a remarkable achievement in history's most crowded electromagnetic environment, and it went almost unnoticed because it simply worked. The Army pooled 1,000 FMSCR 610 radios as insurance against enemy AM jamming during the assault phase. American planners understood that the Germans might try to jam their communications. FM provided inherent resistance to jamming that AM could not match. The beaches were chaos. Men died in the surf. Equipment was lost. Units landed in the wrong places. But communications held. Commanders could speak to their subordinates. Forward observers could reach the fleet. Artillery ships could receive targeting data. The invisible web of radio links that connected all elements of the invasion force remained intact because American FM radios worked when AM radios would have failed. During the Battle of the Bulge, the SCR-300 became what one source called key equipment in preventing confusion during the German offensive. Bad flying weather and dense forest canopy grounded Allied air support for critical days. The fog and low clouds that hampered aircraft also disrupted visual signaling. Ground-based forward observers with radio links became the primary means of directing devastating American artillery fire against the German advance. Without those radios, the German breakthrough might have succeeded. The panzers that broke through American lines were stopped not by aircraft but by artillery directed by observers using FM radios. In the Pacific, the SCR-300 proved essential in jungle terrain, where line of sight was limited and wire communication was constantly severed by artillery, wildlife, and rot. Telephone wire strung through jungle was cut within hours by creatures ranging from rats to elephants. Radio was the only reliable means of communication in such conditions. After the disastrous performance of AM radios at Tarawa in November 1943, the Marine Corps discarded its AM equipment entirely and adopted Army FM sets. It was a decisive institutional endorsement of FM's superiority. The Marines had learned the hard way what happened when communications failed under fire. They were not willing to suffer those failures again. The men who designed these radios faced their own struggles. Henryk Magnuski, the Polish engineer who holds 3 patents on the SCR-300, worked knowing his homeland was under Nazi occupation and his family was in danger. He poured that knowledge into his work. Every circuit he designed, every problem he solved, brought the defeat of Nazi Germany closer. Edwin Armstrong, whose FM technology made the SCR-300 possible, faced a different kind of tragedy. After the war, RCA chose to prioritize television over FM radio. David Sarnoff, head of RCA and once Armstrong's close friend, blocked FM's commercial development. RCA successfully lobbied the FCC to shift the FM band from 42 to 50 MHz to 88 to 108 MHz, rendering approximately 400,000 existing FM receivers obsolete. RCA then claimed its own FM patent and used the technology without paying royalties. Armstrong filed suit in 1948. The litigation consumed his fortune and health. On January 31, 1954, Edwin Howard Armstrong jumped to his death from his 13th floor apartment in Manhattan. His wife Marion eventually won over $10 million in settlements from 21 infringement suits, vindicating his legacy. But the inventor of the technology that helped win the war died broken by legal battles against a company that owed its radio business to his genius. Daniel Noble continued at Motorola after the war, eventually becoming chairman of the board. The company he helped build became one of the giants of American electronics, developing technologies from pagers to cell phones. Henryk Magnuski remained in America, unable to return to communist Poland after the Soviets replaced the Nazis. He continued working as an engineer until his retirement, his contribution to victory largely forgotten by the public, but remembered by those who understood radio technology. The radios themselves passed into history. The SCR-300 was eventually replaced by newer designs. The SCR-536 became a collector's item, sought after by military antiques enthusiasts. A few still work, their tubes still glowing after 80 years. They are artifacts of a moment when American innovation, American industry, and American determination combined to produce tools of war that their enemies could not match. The German experts who examined that captured radio in Sicily in 1943 were looking at more than a piece of equipment. They were looking at the evidence of an industrial and technological gap that Germany could never close. Their country had brilliant engineers and brave soldiers, but America had something Germany lacked: an electronics industry shaped by decades of consumer market competition, a culture of innovation driven by commercial pressure. Tens of thousands of amateur radio operators who understood the technology from practical experience, and an inventor named Edwin Armstrong who gave his country a revolutionary technology and asked nothing in return. The gap that mattered most was not any single specification, but what radio density enabled at the tactical level. Consider what this meant in practical terms. A German company commander spots American tanks approaching his position. He needs artillery support. He sends a runner to battalion headquarters with the request. The runner takes 5 minutes to reach headquarters, assuming he survives the journey across open ground. Battalion staff assess the request and forward it to the artillery. Another 5 minutes. The artillery calculates firing solutions and begins to shoot. By the time shells begin falling, 15 or 20 minutes have passed. The American tanks are no longer where they were reported. The fire falls on empty ground. An American company commander spots German tanks approaching his position. He speaks into his SCR-300. The message reaches a forward observer within seconds. The forward observer radios the fire direction center. Within minutes, artillery shells are falling on the exact position of the German tanks because the forward observer can see them and adjust fire in real time. The German tanks are destroyed before they can close with the American position. This scenario repeated itself thousands of times across every theater of the war. The Americans could observe, report, and respond faster than the Germans because their communications technology enabled a speed of coordination that German equipment could not match. It was not that German soldiers were less brave or German officers less competent. They simply could not process information and respond to changing situations as quickly as Americans equipped with FM radios. The evidence is documented in primary sources that survive to this day. Albert Prawn's report is available from the National Security Agency. The Signal Corps assessments are preserved in military archives. The technical specifications of both American and German radios can be verified from original manuals. The story is not mythology. It is history, recorded by the participants and verifiable by anyone willing to examine the records. Nations still underestimate their adversaries. Leaders still confuse their assumptions with reality. The German High Command believed what it wanted to believe about American industry and technology. They saw what they expected to see rather than what actually existed. The cost of that misjudgment was measured in battlefields lost, campaigns failed, and ultimately in the total defeat of Nazi Germany. The factories that built the SCR-300 and SCR-536 are mostly gone now. The Galvin manufacturing plant on Augusta Boulevard in Chicago has long since been replaced. Fort Monmouth was closed by the Base Realignment and Closure Commission in 2011. The engineers who designed these radios have passed away. Henryk Magnuski died in 1978. Daniel Noble died in 1980. The soldiers who carried these radios into battle grow fewer each year, but the lessons remain. Wars are not won only by courage and determination. They are won by the quiet work of engineers and factory workers, by inventors who solve problems others thought impossible, by industries that can produce not just weapons but the technologies that make weapons effective. Edwin Armstrong invented a technology that saved countless lives, and his own country's corporations drove him to suicide. Henryk Magnuski fled one tyranny only to help defeat another, and then could not return to his homeland because a new tyranny had replaced the old. The history of technology is often a history of human tragedy alongside human achievement. A handheld radio that weighed 5 pounds, a backpack radio that cut through static. These were the tools that helped defeat Nazi Germany. They deserve to be remembered. If you found this story as compelling as we did, please take a moment to like this video. It helps us share more forgotten stories from the Second World War. Subscribe to stay connected with these untold histories. Each one matters, each one deserves to be remembered, and we would love to hear from you. Leave a comment below telling us where you are watching from. Our community spans the globe, from veterans to history enthusiasts. You are part of something special here. Thank you for watching, and thank you for keeping these stories alive.
The year is 1978. The location is the deep, crushing darkness of the North Atlantic, specifically the region known to naval strategists as the Bermuda Box. This is a massive expanse of ocean off the eastern coast of the United States, a patrol zone where the fate of the world hangs in a delicate, silent balance. Down here, 400 meters beneath the surface, the pressure is enough to snap a human spine like a dry twig. But for the crew of the Soviet strategic missile submarine, a Project 667 Navaga, known to the West as the Yankee class, this pressure is home. Captain First Rank Valery Zhuravlev stands in the command center. The air is thick, recycled, smelling faintly of ozone, diesel oil, and the sweat of 120 men living in a steel tube. The lighting is dim, casting long shadows over the dials and gauges that are the eyes and ears of his vessel. Zhuravlev is a veteran. He knows his boat. He knows that the Navaga is a masterpiece of Soviet engineering, a vessel capable of carrying 16 R-27 Zib ballistic missiles, each one tipping the scales of global power. His orders are simple yet terrifying. Remain invisible, patrol the American coast, and wait for the order that he hopes will never come. To Captain Zhuravlev, his submarine is a predator. He believes he is a ghost in the water, sliding through the thermal layers of the Atlantic, undetectable. He believes the Americans are up there, on the surface, scanning with their radar and their satellites, looking for a wake that isn't there. He is confident. But then, the impossible happens. It does not begin with an explosion. It does not begin with a siren. It begins with a hesitation in the rhythm of the ocean. The sonar operator, a young warrant officer named Petrov, lifts his headphones, his face pale in the green wash of the scope. He looks at the captain. He does not speak immediately. In the silent service, you do not speak until you are certain, because uncertainty breeds panic. "Comrade Captain," Petrov whispers, pressing the headphones back to his ears, as if trying to physically push the sound into his brain. "I have a transient, astern, in the baffles." Zhuravlev moves to the station. "Identify." "Gone," Petrov says, his voice trembling slightly. It was a mechanical transient, a metal click, like a hatch closing, but faint, ghostly. Zhuravlev frowns. The baffles, the blind spot directly behind the submarine where the churn of their own twin propellers and the roar of the turbulent water creates a cone of deafness. Nothing can see through the baffles. Nothing should be in the baffles. To be in the baffles of a moving submarine, an object would have to be matching their speed perfectly, maneuvering with impossible precision in the blind, churning wake of a two-propeller drive. "Biological?" Zhuravlev asks. The ocean is full of noises, whales, snapping shrimp, thermal layers shifting. "No, Captain, it was rhythmic. Then it vanished." Zhuravlev orders a standard check. They are running quiet, or so they think. The Yankee class is powerful, but it is not silent. It hums with the brute force of its reactors. The captain dismisses it. It must be a biological anomaly or a reflection from the seabed. a thermal layer bouncing their own noise back at them. Hours pass. The submarine continues its patrol pattern, but the mood in the command center has shifted. The air feels heavier. Then, it happens again. This time, it is not a sound. It is a sensation. The boat shifts slightly, caught in a current that shouldn't be there. The hydrodynamics of the water around them feel wrong. Petrov at the sonar station stiffens. "Contact!" he hisses. "Transient signal, very close, astern, It sounded like a flow noise, something displaced the water." Zhuravlev feels a cold prickle on the back of his neck. He looks at the depth gauge. They are deep. There are no surface ships here. There are no fishing trawlers. If there is something displacing water directly behind them, it has to be submerged. "Perform a check turn," Zhuravlev orders. This is a standard maneuver. The submarine turns roughly to the side to clear the blind spot, allowing the sonar to sweep the area that was previously hidden by the engine noise. The hull groans as the rudder bites into the black water. The submarine banks. The sonar array sweeps the dark ocean behind them. Silence. The green line on the screen revolves endlessly, painting nothing but the empty, cold void of the Atlantic. No contacts, no metal signatures, no engine hum. "Clear, Captain," Petrov reports, but he sounds unconvinced. "The ocean is empty." Zhuravlev exhales. Of course it is empty. It had to be a glitch, a phantom echo. He orders the boat back to its original course. They return to the patrol, but the mystery does not leave them. Over the next 48 hours, the impossible events compound. It becomes a psychological torture. At one point, the passive sonar picks up a strange hole in the ocean background noise. It is as if a massive object is moving through the water, blocking the ambient sounds of the sea, yet emitting no noise of its own. A black hole in the soundscape. How can a machine of war, made of steel and valves and pumps, move without sound? It defies the laws of physics as the Soviets understand them. The crew begins to whisper. They talk of American secret weapons. They talk of sea monsters. They talk of their own equipment failing. The political officer tries to maintain discipline, lecturing them on the superiority of Soviet technology. But even he looks at the bulkheads with suspicion. Zhuravlev stands by the periscope well, though they are far too deep to use it. He runs the scenario through his mind. If there was a vessel there, he would hear it. American submarines are nuclear. They have pumps. They have coolant loops. They have reduction gears. They make noise. To be that close, to be right on top of them, the noise should be deafening. If they are there, and they are silent, then everything Zhuravlev knows about naval warfare is a lie. Then comes the incident that nearly breaks them. It is day 3 of the ghost phenomenon. The sea is rough far above, but calm down here. Suddenly, the sonar shack erupts. "High-frequency ping, single burst, close range." Zhuravlev spins around. An active sonar ping is an act of aggression. It is a shout in a dark room. Someone is painting them. "Range and bearing?" "Directly below us, Captain. Range 0. The command center freezes. 0 range? That is impossible. That would mean the source is touching the hull. "It's gone," Petrov whispers, terrified. "Just one ping, like they were checking the distance." Zhuravlev grips the railing. His heart is hammering against his ribs. This is not a glitch. This is intelligence. Something is out there. Something is toying with them. It is watching them, measuring them, perhaps even touching them, and yet it refuses to be seen. The fear is not just about being found. It is about the total inability to understand what found them. Before we dive deeper into this underwater nightmare and the technological revelation that changed the Cold War, if you are enjoying this investigation into history's hidden conflicts, please verify your subscription to the channel Cold War Chronicles. We declassify the past to understand the present. The stakes for Captain Zhuravlev could not be higher. You must understand what his submarine represents. This is not just a ship. It is a component of the Soviet Union's nuclear triad. The entire strategy of mutually assured destruction relies on the fact that these submarines cannot be found. If the Americans can find a Yankee-class submarine in the open ocean, track it, and remain invisible while doing so, then the Soviet nuclear deterrent is effectively worthless. If the Americans can kill the boomers before they launch, the balance of power collapses. Zhuravlev knows this. He knows that if he reports a ghost, he will be laughed at by the Admiralty. They will say he is hallucinating. They will say he is unfit for command. But if he ignores it, and there really is a threat, he endangers the motherland. He is trapped in a paradox. He is the captain of the most powerful weapon system on Earth, yet he feels like a blind man walking through a room full of razors. He orders another turn, more aggressive this time, a crazy Ivan. A sharp, sudden turn designed to catch a shadower off guard, forcing them to turn hard to avoid a collision, thereby revealing their position with a burst of cavitation noise. The Yankee-class lurches, plates groan, the crew grabs onto stanchions. The submarine swings 180 degrees, its sonar clearing the baffles violently. They listen. They wait for the screech of a propeller, the panic of a sudden turn, the sound of an American sub trying to brake. Nothing, just the hiss of the water. "Nothing, Captain," Petrov says, defeated. "We are chasing shadows." Zhuravlev stares at the sonar screen. He wants to believe it. He wants to believe the ocean is empty. But deep down, a cold dread is settling in his gut. He realizes that the silence is not proof of safety. The silence is the threat. Because if there is a machine out there that can dance with a turning submarine, match its erratic movements, and remain quieter than the background noise of the Atlantic Ocean, then the Soviet Union has already lost the war at sea. They just don't know it yet. The captain does not know that a few hundred yards away, separated by a wall of water and a chasm of technology, a tape recorder is spinning, capturing every groan, every pump cycle, and every word spoken aboard his ship. He does not know that he is not the hunter. He is the prey, and the hunt has been going on for days. Captain Zhuravlev returns to port in the grey, freezing waters of the Kola Peninsula. The submarine base at Gadjievo is a bleak landscape of concrete, rusting cranes, and snow. The mood on the dock is somber. The mission was technically a success. They patrolled, they remained unengaged, they returned. But the psychological toll on the command crew is visible. They look like men who have seen a ghost. The investigation begins not with a scientific inquiry, but with an interrogation. In a windowless room smelling of stale tobacco smoke and wet wool, Zhuravlev faces a panel of senior officers from the Northern Fleet and a representative from the GRU, Soviet Military Intelligence. The Soviet system does not reward unexplained phenomena. Unexplained phenomena are treated as errors, and errors are treated as crimes. "Repeat your statement, Captain," the Admiral says, tapping a thick file on the metal table. "You claim you were tracked for 3 days by a vessel that showed no sonar return, made no engine noise, and could maneuver in your baffles while you performed evasive turns." "Yes, Comrade Admiral," Zhuravlev says, keeping his voice steady. "And yet," the Admiral continues, leaning forward, "your acoustic tapes show nothing, just the ocean, just the background noise of the Atlantic. Are we to believe in phantoms? Or are we to believe that your sonar operators were hallucinating from fatigue?" This is the Soviet dilemma. The evidence of the American presence is negative evidence. It is the absence of normal readings that terrified the captain, but bureaucracy demands positive proof. The tapes are played again. The room fills with the hiss of static. The experts point to the spikes on the graph. "Here," the acoustic analyst says, pointing to a jagged line, "biological, likely a pod of whales. And here, thermal layer distortion." The captain interpreted natural oceanography as a hostile contact. The verdict is humiliating, but predictable. Pilot error. Paranoia. The crew is reprimanded for filing false reports. Zhuravlev is not stripped of command, but a black mark is placed next to his name. He is sent back out to sea. But Zhuravlev is not the only one. As the months of 1978 turn into 1979, a pattern begins to emerge that the Admiralty can no longer ignore. Reports start filtering in from other Yankee and Delta-class boat commanders. They are fragmented, whispered in officers' messes, and filed in classified folders that are slowly stacking up in Moscow. One commander reports a collision alarm screaming in deep water, only for the sensors to show empty ocean seconds later. Another reports hearing machinery noises, clearly through the hull while sitting stationary on the seabed. Noises that sounded like a reactor pump, but far too quiet to be one of theirs. A legend begins to build within the Soviet Navy. They call it the Shadow. The Soviet response is a massive, frantic, but fundamentally flawed investigation. They form a special technical commission to identify the source of these anomalies. But because they cannot conceive that the Americans have achieved total acoustic invisibility, they look for other answers. They look for the enemy everywhere except where the enemy actually is, in the technology gap. First, they blame the equipment. The Soviet naval doctrine relies heavily on the brute force of their sonar arrays. They believe their sensors are powerful, perhaps too powerful, picking up ghosts in the data processing. Teams of engineers descend on the submarines in dry dock. They tear apart the sonar consoles, rewiring them, replacing valves with solid-state transistors, trying to filter out the hallucinations. They tighten the sensitivity thresholds. Ironically, by reducing the sensitivity to eliminate ghosts, they make their submarines even blinder. They are effectively putting on darker sunglasses to stop seeing flashes of light. Next, they blame sabotage. The paranoia of the Cold War takes a dark turn. The KGB becomes involved. If the Americans are tracking them, they reason, it cannot be because American subs are invisible. It must be because the Soviet subs are carrying a beacon. A period of intense, invasive physical searches begins. This is the era of the hull sweeps. Before a strategic missile submarine leaves port, frogmen are sent into the freezing water to scour every inch of the hull. They are looking for magnetic trackers, limpet mines, or transponders attached by American spies or saboteurs. Inside the boat, counterintelligence officers rip up floor plates and dismantle radios, searching for a transmitter that might be broadcasting their position to a satellite. They find nothing. The investigation then turns to the realm of the exotic. Soviet scientists, desperate to provide an answer that doesn't involve American superiority, propose wild theories. One leading theory is that the Americans have developed a network of seabed sensors so advanced that they can track the displacement of water itself. They theorize that the Americans aren't tracking the sound of the sub, but the pressure wave it pushes through the ocean. If this were true, no amount of silencing would help. Another theory suggests the Americans are using a new type of radar satellite that can penetrate the ocean's surface, seeing the submarine's wake from space. This leads to the Soviets experimenting with strange paint schemes and wake suppression tactics, wasting millions of rubles on solving a problem that doesn't exist. The tragedy of the Soviet investigation is that they are asking the right question: how are they finding us? But they are refusing to accept the answer. The answer is that the ocean is a sound channel, and the Soviet submarines are simply too loud. To the Soviet Admiralty, a submarine is a machine of power. It has 2 nuclear reactors. It has 2 massive propellers. It is a beast. To make it silent seems counterintuitive to the philosophy of Soviet heavy industry. They believe that noise is a byproduct of power. They assume the Americans are subject to the same laws of physics. If a Soviet sub hums, an American sub must hum. They do not understand the concept of rafting, the American technique of isolating the entire engine room on rubber mounts so that no metal touches the hull. To a Soviet engineer in 1979, placing a nuclear reactor on rubber shock absorbers sounds like madness, a structural weakness waiting to collapse. So, they double down on their existing doctrine. The investigation concludes that the Shadow is a combination of natural phenomena and aggressive American surface tactics. They decide that since they cannot hide, they must run. New orders are issued to the fleet. If you suspect a contact, do not go quiet. Go fast. Go deep. The Soviet strategy shifts to speed and depth. They begin pushing the designs for the next generation of submarines, titans like the Typhoon and speed demons like the Alpha class, believing that they can outrun the ghosts. They instruct their captains to use active sonar more frequently, to blast the water to clear it. This is a catastrophic error. By going faster, they make more noise. By using active sonar, they act like a burglar turning on a flashlight in a dark house, instantly revealing their position to everyone in the neighborhood. While the Soviet committees argue in Moscow, analyzing charts and blaming sunspots, the crews on the front lines are left in a state of high anxiety. The sailors know the truth. They know the ghosts are real machines. In the mess hall of a Delta III submarine, a sonarman whispers to his friend, "It's not a satellite," he says, staring into his tea. "I heard it breathe. When we stopped, it stopped. When we moved, it moved. It's a hunter, and it's laughing at us." The investigation has failed. The Soviets have convinced themselves that the threat is external. Satellites, spies, sabotage. They have failed to look in the mirror. They have failed to realize that their silent service is screaming into the void. And while they spend billions chasing wake detection satellites and magnetic mines, a small group of engineers in the United States Navy is preparing to launch the very thing the Soviets believe is impossible. The Soviets are looking for a new weapon. They are about to be hit by a new philosophy. The stage is set. The Soviets are confused, paranoid, and looking in the wrong direction. The ocean is about to get much more crowded, and the predator is about to reveal its teeth. But it won't be a monster. It will be a machine so precisely engineered that it effectively removes itself from the universe of sound. While the Kremlin was paralyzed by paranoia, conducting witch hunts for saboteurs and theorizing about space lasers, the answer to the mystery was sitting quietly in a dry dock 4,000 miles away. The location is Groton, Connecticut, the General Dynamics electric boat shipyards. The year is 1976. If the Soviet submarine program was a forge of brute industrial strength, designed to punch through the ocean, the American program was becoming a laboratory of silence. In a restricted hangar, illuminated by the sparks of welders and the hum of ventilation, American engineers were putting the finishing touches on a machine that would redefine naval warfare. They called it the 688 class, the Los Angeles class. To the untrained eye, it looked like any other submarine, a black steel cylinder. But inside the hull, the philosophy of construction was alien to the Soviet mind. The Americans had realized decades earlier that in the nuclear age, speed was secondary to stealth. If you are fast but loud, you are just a noisy target. If you are slow but silent, you are a hole in the water. The secret to the ghost that terrified Captain Jуравлев lay in a concept known as rafting. In a Soviet submarine of this era, the massive turbines, the reduction gears, and the pumps were bolted directly to the hull frames. When a Soviet turbine spun, the vibration traveled through the bolt, into the hull steel, and radiated out into the ocean like a bell ringing. This is why Jуравлев's boat hummed. It was a ringing bell. The engineers of the 688 class did something radical. They built the entire engine room, hundreds of tons of machinery, on a floating platform inside the submarine. This platform, or raft, sat on complex rubberized sound isolation mounts. The machinery never touched the hull. The vibration was absorbed by the rubber. The hull remained dead. The Los Angeles class was not just a ship. It was a thermos bottle of sound. A sailor could drop a wrench in the engine room, and a sonar operator on a ship 10 miles away would hear nothing. But silence was only half of the equation. To be a true ghost, you need to see without being seen. And this is where the American technological dominance truly left the Soviets in the Dark Ages. The Soviet investigation in Part 2 failed because they assumed the Americans were limited by the same physics. specifically the problem of the baffles, the blind spot behind the sub. They assumed that to track Zhuravlev, the American sub had to be on the side or in front. They were wrong. The Americans had deployed the AN/BQQ-5 sonar suite and, crucially, the towed array. Imagine a thick, black cable, over half a mile long, spooling out from the tail of the American submarine. This cable is studded with hydrophones, underwater microphones. By trailing this cable far behind the submarine, the sensors are removed from the noise of the sub's own propeller. They are out in the clean, quiet water. This was the magic that allowed the Americans to see through the blind spot. The Los Angeles class didn't need to move to the side to listen. It could sit directly behind a Soviet sub, trailing its long ear miles back, listening to the Soviet captain breathe, while the Soviet sonar looked backward and saw nothing but the empty wake. Let us shift our perspective to the hunter. Meet Commander James "Red" Harrison, a composite of the era's aggressive skippers. He is the commanding officer of the USS Batfish, a Sturgeon-class attack submarine, the predecessor to the 688, but upgraded with the new ears. The scene in Harrison's attack center is the polar opposite of Zhuravlev's. It is not dim and sweaty. It is cool, lit by the blue glow of digital fire control screens. There is no shouting. The discipline is absolute. "Con, sonar," the voice comes over the headset. "Contact Sierra 1 is steady. Range 4,000 yards. Classification: Yankee-class nuclear ballistic missile submarine." Harrison sits in his chair, sipping coffee. He is not looking at a periscope. He is looking at a waterfall display, a cascading digital readout of sound frequency. To him, the Soviet sub is not a mystery. It is a loud, clanking factory. He can see the frequency line of their 50 Hz power plant. He can hear the specific rattle of a loose bearing on their starboard shaft. He knows the Soviet sub better than its own captain does. "Very well," Harrison says softly. "Maintain trail position. Stay in his baffles. Match speed. 6 knots." This is the impossible event from Part 1, seen from the other side. The Ghost was simply a highly trained American crew, utilizing superior physics to sit in the one spot the Soviets thought was safe. When Zhuravlev ordered his check turn, swinging his boat to the right to clear his blind spot, he thought he was being clever. On the American sub, the sonar computer instantly registered the change in the Soviets' propeller pitch. "Sierra 1 is shifting rudder," the sonar chief reports casually. "He's clearing his baffles. Crazy Ivan to starboard." "Gentle rudder left," Harrison orders. "Drift out. Let him pass." The American sub, silent on its rubber mounts, simply glides to the side. The Soviet active sonar blast, the ping that terrified Zhuravlev, hits nothing but empty water, because the American sub has already anticipated the move. They are dancing a waltz, but only one partner knows the steps. The American sub slides back into position behind the Soviet vessel as soon as it straightens out. It was a game of cat and mouse, but the mouse was blindfolded, and the cat was wearing night vision goggles. But the American advantage went deeper than just hardware. It was computational. In the late 1970s, the Soviet Union was lagging severely in microcomputing. Their sonar processing was largely analog. It required human operators to stare at raw oscilloscope waves to interpret sound. The Americans were digitizing the ocean. The computers aboard the Los Angeles class could take millions of bits of acoustic data and filter it. They could subtract the sound of rain, the sound of shrimp, the sound of waves, leaving only the artificial frequency of the enemy machine. This allowed the Americans to do something terrifying: target motion analysis without ever emitting a ping. They could calculate the exact range, speed, and depth of the Soviet sub using only math and passive listening. They could generate a firing solution for a Mark 48 torpedo that would guide the weapon to the target before the Soviet captain even knew he was under attack. The transient noises Zhuravlev heard, the click of a hatch, that was likely the sound of the American crew going about their daily lives, Perhaps a drop tray in the galley or a toilet flush valve, noises that were usually silenced but occasionally slipped out. The fact that Zhuravlev heard a toilet flush, but not the 6,000-ton submarine carrying it, is a testament to how quiet the hull itself was. The American mission during this period was known as Hold Down. The objective was to prove that the Atlantic Ocean was a NATO lake. Every time a Soviet missile sub left the Kola Peninsula, an American attack sub would be waiting at the choke point, the GIUK Gap, Greenland, Iceland, United Kingdom. They would pick up the trail and never let go. For days, sometimes weeks, the American sub would shadow the Soviet boat. They would record their noise signatures. They would map their patrol patterns. They would practice simulated shots. To the American crews, this was a point of immense professional pride. They were the cowboys of the deep. They wore sneakers to reduce noise. They grew beards. They worked 18-hour days. And they knew they were invincible. But there was a danger in this dominance. The Americans became so good, so confident in their invisibility, that they began to take risks. They got closer and closer. They wanted to see how much they could get away with. The hole in the ocean that the Soviets detected in Part 1, that wasn't a glitch. That was the physical displacement of the American submarine getting so close to the Soviet hull, sometimes within a few hundred yards, that it actually blocked the background noise of the sea. They were drafting like a race car in the wake of the enemy. This secret war continued in the dark, a total triumph of American engineering and daring. The Soviets were spending billions on the wrong things, chasing phantoms, while the Americans were essentially reading their mail over their shoulders. However, secrets in the Cold War have a shelf life. The Americans thought this technological gap would last forever. They thought the Soviets were simply too far behind to catch up. They believed their acoustic daylight would never dim. But a chain is only as strong as its weakest link. And the weakest link in this story wasn't a piece of technology. It wasn't a sonar equation. It was a human being. The Soviets were about to get the answer they had been desperately searching for, not from a scientist and not from a spy satellite. They were about to get it from a traitor who walked right through the front door of the Soviet embassy in Washington, D.C., and handed them the keys to the kingdom. The shock is coming, the moment the Soviets realized just how naked they really were. The mystery of the shadow was not solved in the North Atlantic. It was solved in a nondescript room in Moscow, under the harsh glare of a fluorescent light amidst a pile of stolen documents. The year is 1981. The breakthrough did not come from a Soviet scientist inventing a new sensor. It came from an American traitor named John Anthony Walker. Walker was a chief warrant officer in the United States Navy. For over a decade, he had been walking into Soviet embassies and handing over key lists, technical manuals, and tactical diagrams in exchange for cash. He is often cited as the most damaging spy in American naval history. But among the codes and the cipher keys, he handed the KGB something far more devastating: the blueprints of the American acoustic advantage. The shock moment occurred when a team of senior Soviet naval architects and KGB analysts finally sat down to correlate Walker's stolen data with the reports from captains like Zhuravlev. For years, the Soviet Admiralty had convinced themselves that the Americans were using some exotic, undetected physical principle to track them, perhaps radiation detectors or wake sensors. Walker's documents shattered this delusion. The documents revealed that there was no magic. There was no super sensor. The Americans were simply listening to the propellers. Specifically, Walker revealed that the Americans could detect cavitation at ranges the Soviets thought were impossible. Cavitation occurs when a propeller spins so fast that it creates low-pressure bubbles in the water. When these bubbles collapse, they snap shut with a loud acoustic crack. The Soviet engineers stared at the stolen charts in horror. The data showed that American attack submarines could classify a Soviet sub's individual propeller blade rate from 50 miles away. They could tell if a shaft was slightly misaligned. They could even identify individual vessels based on the specific rhythm of their engine room pumps. Admiral Gorshkov, the father of the Soviet Navy, reportedly read the assessment and turned pale. The realization was absolute and terrifying. The entire Soviet submarine fleet, hundreds of vessels, billions of rubles, the pride of the superpower, was not a stealth force. It was a fleet of drums banging in a library. Captain Zhuravlev's experience was finally explained. The transient sounds he heard? That was the American sub Batfish maneuvering close to him. The reason the ghost disappeared when he turned? The Americans knew his blind spots better than he did. The reason they couldn't find a tracking device on his hull? There was no device. The submarine itself was the beacon. This was the Pearl Harbor of the Soviet Navy, but it happened without a single shot being fired. They realized that in the event of a real war, their entire ballistic missile fleet, the insurance policy of the Soviet Union, would have been wiped out in the first 48 hours. The Americans would have been waiting in the baffles, ready to fire a torpedo the moment the order came. The balance of terror was a myth. The Americans held the gun to the Soviet head, and the Soviets hadn't even known it was loaded. Now came the panic. The response was frantic and desperate. The Soviet military-industrial complex, now aware of the fatal flaw, launched an emergency program to quiet their fleet. But they hit a technological wall. Their heavy industry was excellent at casting steel, but it lacked the precision required to make silent propellers. To make a silent propeller, you need to machine the bronze blades to a tolerance of less than a fraction of a millimeter. The curve must be perfect to slice the water without creating bubbles. Soviet milling machines were simply not accurate enough. They were stuck in the industrial age, while the Americans were in the digital age. This led to one of the most audacious and desperate operations of the Cold War, the Toshiba-Kongsberg scandal. In 1982, knowing they could not build the machines themselves, Soviet agents approached the Japanese company Toshiba and the Norwegian company Kongsberg. Through a complex web of lies and falsified export documents, they illegally purchased 9-axis computer-controlled milling machines, technology that was strictly embargoed by COCOM, the Coordinating Committee for Multilateral Export Controls. These massive machines were smuggled into the Soviet Union. They were set up in the Baltic shipyard in Leningrad. For the first time, Soviet engineers could carve propellers with the same computer-aided precision as the Americans. The impact was immediate. The new propellers were fitted to the next generation of submarines, the Akula class, Shark, and the upgraded Victor III class. When these new boats put to sea in the mid-1980s, the American advantage suddenly shrank. The acoustic daylight began to dim. American sonar operators, used to hearing Soviet subs from counties away, suddenly found themselves having to work harder. The loud banging was replaced by a faint hum. But this was a futile response. It was a band-aid on a hemorrhage. The shock had come too late. By the time the Soviets began quieting their propellers in the mid-80s, the American economy and technology had already leapt forward again. While the Soviets were celebrating their new, quieter propellers, the Americans were deploying the next nightmare: active denial. They were integrating satellite oceanography, magnetic anomaly detection, and advanced computer processing that could pick up the absence of background noise. Furthermore, the strategic damage was already done. The Soviet leadership had lost faith in their own deterrent. The psychological impact of the Walker revelation crippled their confidence. They shifted their strategy from open ocean patrol to the bastion concept. Instead of prowling the Atlantic and threatening the US coast, Soviet missile subs were ordered to retreat. They pulled back into the Barents Sea and the Sea of Okhotsk, hiding under the Arctic ice cap, protected by a ring of surface ships and aircraft. This was a retreat. It was an admission of defeat. The Blue Water Navy that Gorshkov had dreamed of, a navy that could challenge the Americans anywhere on the globe, was dead. They were forced to hide in their own backyard because they knew that out in the deep water, the shadow was waiting for them. The futile nature of their response was best summarized by a defecting Soviet officer years later. He noted that while the Toshiba machines made the propellers quieter, they couldn't fix the pumps, the gears, or the reactor flow noise without rebuilding the entire submarine from scratch. You can put silent tires on a noisy truck, but the engine will still rattle. The Soviets spent the last decade of the Cold War frantically trying to patch a hole in their defenses that was systemic. They built bigger subs, like the massive Typhoon, hoping that size and armor would save them. They built faster subs, but they could never replicate the culture of silence and the precision engineering that the Americans had perfected over 30 years. The impossible event that Captain Zhuravlev witnessed in 1978 was the precursor to the collapse of the Soviet system itself. It was a confrontation between a society built on quotas and heavy metal and a society built on microchips and precision. The mystery was solved. The ghost was real, and it was made in America. But the true legacy of this encounter would only be fully understood when the Soviet Union finally fell, and the archives were opened to reveal just how one-sided the underwater war had really been. The Cold War did not end with a nuclear mushroom cloud rising over New York or Moscow. It ended in the accountant's ledger, and nowhere was the deficit more terrifyingly obvious than in the silent war beneath the waves. The verdict of this decades-long game of cat and mouse can be summarized in one devastating statistic, a number that remained classified top secret until long after the Berlin Wall fell. In the mid-1980s, following the revelations of the Walkie spying and the analysis of Soviet exercises, American naval strategists ran a computer simulation of World War III. The parameters were simple. The Soviet Union launches a first strike. What happens to their submarines in the Atlantic? The result was a kill ratio that stunned even the most hawkish generals in the Pentagon. The simulation predicted that within the first 4 hours of hostilities, before they could even complete their firing sequences, over 90% of Soviet Yankee and Delta-class submarines in the Atlantic would be destroyed. 90%. This is the killer statistic. It renders the trillions of rubles spent by the Soviet Union on their naval expansion effectively wasted. They had built the largest submarine fleet in human history. They had launched hundreds of hulls. They had trained thousands of officers, like Captain Zhuravlev. They had created a force that looked terrifying on paper and in May Day parades. But in reality, they had built a fleet of floating coffins. The ghost that Zhuravlev encountered, the American attack submarine sitting in his baffles, was not an isolated incident. It was the standard operating procedure. For nearly 2 decades, the United States Navy had achieved a level of dominance that is rare in the history of warfare. It was akin to an army marching into battle with invisible tanks. The impact of this realization on the Soviet Union cannot be overstated. It broke the back of their strategic confidence. When the Soviet leadership realized that their blue water navy could not survive in the open ocean, they were forced into the bastion strategy we discussed in Part 4. But the economic consequences of this retreat were fatal. Because they had to hide their submarines in the Barents Sea, thousands of miles further away from the American coast than the Bermuda Box, their old missiles could no longer reach targets in the United States. To hit Washington, D.C. from the Arctic, they needed bigger, heavier, longer-range missiles. To carry these massive new missiles, they had to build massive new submarines. This birthed the Typhoon class, the Project 941 Akula. It remains the largest submarine ever built. It was a titan of steel, twice the size of its American counterparts, featuring swimming pools and saunas for the crew. It was a marvel of Soviet heavy industry, but it was also a catastrophic economic black hole. One Typhoon-class submarine cost as much to build as an entire city, and the Soviets built 6 of them. They were pouring concrete into the ocean, while the United States was investing in the microchip, the internet, and the software revolution, technologies that had both military and civilian applications. The Soviet Union was bankrupting itself trying to mill silent propellers and weld titanium hulls just to survive. This connects the mystery of the Phantom Sub to the macro theme of the Soviet collapse, the triumph of software over hardware. The American advantage wasn't that they had better steel, it was that they had better information. The Los Angeles class was a computer with a propeller. The Soviet subs were tanks with periscopes. In the modern age, the computer always wins. The Toshiba Kongsberg scandal was the final admission that the Soviet system had failed. A superpower that can put a man in space but cannot manufacture a silent propeller blade without buying illegal machines from its enemies is not a superpower. It is a hollow giant. The legacy of this underwater conflict shapes our world today. The technology developed to track Juravev, the digital signal processing, the advanced hydrodynamics, the satellite oceanography, didn't just win the war, it laid the groundwork for the modern surveillance state. The ocean, once the last great wilderness where a captain could vanish, became a glass house. And what of the men? Captain Valery Juravev and his generation of commanders were left to watch their empire rust. When the Soviet Union dissolved in 1991, the mighty fleet that had terrorized the Atlantic was abandoned. In the icy ports of the Kola Peninsula, specifically in Olenia Bay, dozens of nuclear submarines were tied up and left to rot. The Yankee-class boats, the very vessels Juravev commanded, were stripped of their missiles. Their reactor cores were removed, often funded by American money under the Nunn-Lugar Cooperative Threat Reduction Program, and their hulls were cut up for scrap. It is a haunting image. The terrifying machines that once held the world hostage, reduced to piles of jagged metal in the snow. The razor blades you used this morning might have once been the hull of a Soviet missile boat that prowled the Bermuda Box. But the true legacy is the silence. If you go to the North Atlantic today, the game continues, but the players have changed. The Russian Federation has rebuilt. Their new Yasen-class submarines are incredibly quiet, utilizing the lessons learned from their humiliations in the 70s and 80s. The gap has closed. The Ghost is no longer the undisputed master of the deep. The ocean is dark again. However, the lesson of 1978 remains relevant. It teaches us that hubris is the most dangerous enemy. The Soviets believed they were strong because they were big. They believed they were safe because they couldn't hear the danger. They ignored the anomalies. They rationalized the ghosts. Captain Juravelev's horror wasn't just about an enemy submarine. It was the horror of a man realizing that his entire worldview was false. He realized that while he was playing checkers, his enemy was playing three-dimensional chess. In the end, the Cold War wasn't won by the missile that was fired. It was won by the missile that didn't need to be fired, because the enemy knew, with absolute certainty, that he was already dead before he could reach for the button. This is Cold War Chronicles. If you enjoyed this deep dive into the invisible war, please subscribe and turn on notifications. We have only just scratched the surface of the secrets buried beneath the ice. Until next time, stay silent, stay deep.